Question. No question? Okay, so we'll continue with the replication today. I have uploaded the slide, so you should do practice. Now, few things about replication which you need to focus is that the mechanism of DNA replication, what chemical reaction goes on, what enzymes and their properties. I think the most important thing which I emphasize on replication is that when DNA is replicated, then it must have to be with high accuracy. So without that, we end up with mutation, which sometimes can be repaired, sometimes cannot be repaired, and there is replication error. If they accumulate with many rounds of replication, eventually it can turn on oncogene in cancer. Correct? So these are some of the stuff we need to remember. So replication is semi-conservative. We discussed in the last class that when double helical DNA is replicated into two duplexes, in each duplex, one of the strands comes from the parent and another strand is complementary strand is new, and this is semi-conservative mode of replication. Replication is bidirectional. When there is replication growing for such a big DNA, replication goes in both directions, correct? So that it can copy large amount of DNA in short time, correct? So bidirectional. And replication is semi-discontinuous. We discussed that there are two strands. One is leading strand, which is continuously replicated, and replication always takes place from 5' to 3' direction. And newly incorporated DNA is always incorporated at the 3' end of the primer. And the other strand, which is we call the lagging strand, because of the direction issue, correct? It cannot be replicated continuously. So the lagging strand falls to put the primer 3' end in the proper direction, but once some part is replicated, polymerase has to move. So leaving whatever is synthesized. So it's kind of semi-discontinuous with the synthesis of Okazaki fragments. So we discussed some of these. Read the biochemical experiments which has been done to prove that they are semi-conservative, they are bidirectional, and so on. So basically, this is the double helical DNA. It needs to open up, unwind, correct? It needs to open up, unwind. We'll talk about something called helicase in next few minutes, few slides down, which helps to open up the DNA so that you have two open single-stranded form and which is elongated with the help of the primer. DNA replication requires a primer. Without the primer, DNA replication cannot take place. When you go to the transcription, you will see that RNA polymerase, which copies DNA into RNA, does not require a primer. Okay? So primer is a short oligonucleotide which is complemented to certain region of the DNA, and this is the new DNA, 3' end is where the new nucleotide is incorporated, and primer is extended from the 5' to 3' direction. But new nucleotides are always added at the 3' end. Does it make sense? So there is a problem in the lagging strand. So because this is 3' end, this is 5' end. In principle, correct? The DNA replication would take place in this direction, so it should go this way. But DNA polymerase binds here and it moves this direction. Does it make sense? So that's why it cannot replicate this way. So to avoid that, to adjust that, this forms a loop so that 3' end of the primer is facing the DNA polymerase which is here. Okay, so that still it adds at the 3' end, but when polymerase likes to move, whatever the DNA is made here, it gets released. That's the eukaryotic fragment. What's the size of the eukaryotic fragment? How big?
2000.
About 2000 base pairs long. It could vary, but in that range. So if you read the biochemical experiment we did yesterday, we showed yesterday that you take E. coli, correct, and add some 32P alpha phosphorus at the alpha position is 32P radial level, and you add that in the beginning and maybe allow it to grow for a minute or two. Then you remove the radioactivity, correct, and then monitor the length of the DNA with time. Beginning you see a large piece of DNA which is lagging strand, and also you see some amount of the 2000 nucleotide long, correct, DNA strand. But with time you see that these radiolabel small eukaryotic fragments are disappearing. Why do they disappear? They get converted into bigger one. Why? Alright? Try to understand these experiments. These are very interesting biochemical experiments. So you have taken the E. coli cell, add 32P DATP for maybe, let's say, 2 minutes. Alright? Alright? So basically the 32P DATP is incorporated within the DNA. Then remove 32P DATP, correct, and monitor the isolate DNA at different time points. How do you remove the 32P DATP? You are growing the cells, you added 32P deoxy ATP. After 2 minutes or so, you remove this DATP, radiolabel DATP. How would you remove? Just change the media, correct? How many of you have worked in a biochemistry lab? You need to get into the lab. You need to get into the lab right now, at least grow the cells, grow the bacteria, clone, because without that you are just stuck in the slides, correct? So get into a functional lab, do something, work something, which is very important. So when you take the bacteria, add the media, they will grow. In the media you add the deoxy ATP. Now 2 minutes later, you just change the media. So all the radioactivity will go away, correct? Add the fresh media, bacteria will grow, and from that you isolate the DNA from the bacteria at different time points. Let's say 30 seconds, 1 minute, 5, 10, 20 minutes. Isolate the DNA and you run the DNA in agar gel. You have taken the biochemistry lab? No. The biochemistry lab we provide, you got to take some time. So you isolate the DNA, you can run the DNA, you can separate the DNA in agar with gel. This is called gel electrophoresis, minus and plus. You load the DNA here. Okay, DNA is negatively charged under the electrophoretic electric field. The negatively charged DNA will move, correct, towards the positive side, and they will separate based on the size and topology. If the DNA is bigger, you will see somewhere here. Correct? If DNA is smaller, you will see something here. Does it make sense? So let's say this is 30 seconds, this is 5 minutes, this is 20 minutes. Okay? You see that this is becoming thin and this is becoming thick, this is becoming thick, like this. Does it make sense? So this is about 2000 nucleotide long. If you do that, this is a radioactivity, so you put autoradiogram them, correct? And with time you see that this band is disappearing. Why it is disappearing? Yeah, they are actually these small fragments which was initially present, eventually they join together, correct? And become big. So these fragments are Okazaki fragments, and this is how the Okazaki discovered that there is short oligonucleotide cell formed, which eventually, correct, ligate to form the big one, and he named them Okazaki fragments. So Okazaki fragments are produced in the lagging strand synthesis, short stretch of oligonucleotides. It's not really short stretch, it's about 2000 nucleotide long, and eventually they get ligated. We'll talk about how they get ligated. So know this mechanism of DNA replication. Now let's talk about a little bit more. So let's take a DNA template, which is 5 prime, 3 prime, and you have a primer which has 3 prime hydroxyl group, and let's say this is P, so this will be A, already end of the primer. So these are complementary, correct? Now let's say the following nucleotide is G, A, C. I take some, correct? Arbitrary nucleotide, which is anything. Now we add GNTP, which has deoxy-ATP, GTP, GTP, CTP, and TTP, correct? All 4 nucleotide triphosphate. You need DNA polymerase and magnesium ion, which is a cofactor. Of course, you put in the buffer, what will happen? The next nucleotide will be O. So CTP will bind, complementary to this, and then it will form the phosphodiester bond. So you will produce PA, C, G, and you have new nucleotide, new 3' end, which is created, which is ready for the next nucleotide incorporation. Is it clear? So this is normal. So this reaction is catalyzed by DNA polymerase. The polymerase activity of the DNA polymerase helps to synthesize this phosphodiester bond. But so this GC pairing is done by the complementary base pairing, correct? So there are binding sites for the nucleotide binding sites in the polymerase, so nucleotide comes and binds. But sometimes by mistake, it happens that instead of CTP, so this is a mistake, that instead of CTP, another nucleotide got incorporated by mistake. So you have T, A, G, instead of C, let's say it became whoever it is, A. Any other nucleotide other than G. So you have a polymerase. You have a polymerase. It has like a hand, palm. It has three different regions. What means palm region, palm, correct, palm and finger region. So there is nucleotide. This is the active site. Also there is nucleotide binding site. DNTP binding site. So basically these DNTP nucleotides are coming and binding there, but C is expected to bind, but sometimes instead of C, correct, we have A comes in and we form A incorporated. It is a mistake, and GA normally do not form a good hydrogen bond, correct? So what will happen under those situations? So you will produce something like T, A, G, A. Did not form that good hydrogen bond. Does it make sense? It does not form that good hydrogen bonding, it remains melted. So if it is melted, that means there is no efficient hydrogen bonding here. DNA polymerase immediately recognizes that it is a mistake. Because if it incorporates A, in next cycle it becomes AT instead of normal GC. So it's a mutation. Does it make sense? So this is a mistake by the polymerase. And once it is done the mistake, the DNA is kind of melted. Hanging, and once it is melted, DNA polymerase recognizes that it is not the right thing, so it has to correct at this point. So there is a phosphodiester bond here, O, P, correct? I'm writing in brief here, we'll do the chemistry with you. So what happens? DNA polymerase corrects it, so it does proofreading. So basically, it hydrolyzes this incorrect nucleotide. So we produce TAOA. Let's make it this way. C. Is it clear? So now again, it removes minus AMP. So this thing is hydrolyzed out, which is wrong nucleotide, and it goes back to the previous form, and now it has a fresh 3' hydroxyl group, lost the incorrect nucleotide incorporation. Now it can start again with the deoxy-CPT correct nucleotide incorporation. Does it make sense? So this process is called proofreading. How it is done? The DNA polymerase incorporates the wrong nucleotide by mistake. Mistake could be 1 in a million, depending on the type of DNA polymerase. It could be 1 in billion, 1 in million, correct? But still it's a mistake. 1 in million is a big mistake. But no enzyme is perfect. So every enzyme has some error, like human, correct? We are not perfect anytime, correct? So DNA polymerase also does the mistake, but it could be 1 in a million, which is highly accurate, but still it does a mistake. But if it does a mistake, it's a big mistake for the DNA because it's a mutation. So under those circumstances, it recognizes the mistake. How it recognizes? Because Ga pair does not form efficient hydrogen bonding, so it remains melted. If it is melted, it recognizes there is something wrong, correct? So now it hydrolyzes out this particular phosphodiester bond. The wrong nucleotides create a fresh 3' hydroxyl group with the correct mismatch. Now it has opportunity to incorporate new correct nucleotide, and DNA polymerase moves on. Okay. So this whole thing is called proofreading. So once the DNA polymerase does a mistake, it hydrolyzes the wrong nucleotide. If it does not hydrolyze, it's a problem. Correct? So this is, if you see, this is 3' end. So this is 3' end, this is 5' end. So hydrolyzing this phosphodiester is correct nuclease activity. So this is 3' to 5' end exonuclease activity. What is the difference between exo and endonuclease? Why we call exonuclease? It is from the end. Exonuclease only works from the end. Correct? It hydrolyzes the terminal nucleotide, and endonucleotide would hydrolyze the phosphodiester bond in the middle of the DNA. So this is an exonuclease, and it is hydrolyzing 3' to 5'. Does it make sense? So this is a 3' to 5' exonuclease activity, which is part of the DNA polymerase. So DNA polymerase will see the crystal structure. It is thumb, palm, and finger region, and this DNA polymerase, within the same polymerase, there is an active site which incorporates polymerase. There is active site which are responsible for exonuclease activity. So it switches. So this is in the polymerase mode. When the polymerase binds here, this is in polymerase active site, and when it is melted, DNA polymerase change the binding to the exonuclease active site. Does it make sense? So DNA polymerase initially was bound in the polymerase active site. Now because there is a melting, it switches the active site into exonuclease. And once it hydrolyzes it, again it goes back to the polymerase active site and does nucleotide incorporation.
Is melting just caused by mismatch?
Yeah. So melting, yeah, mismatch means it does not, correct? Whenever there is a N mismatch, there are a lot of biochemical experiment has been done, proofreading activity was high. So it is a mismatch which is recognized, because there is no other way it can recognize, correct? Okay, so 3' to 5', exonuclease activity serves as a proofreading function. It removes the incorrectly matched bases so that the polymerase can try again. Does it make sense? Yes or no? Now, newly formed strand oscillates between polymerase and exonuclease site. So basically, it switches back and forth, and depending on the link, it binds to a specific active site. So this is a nucleotide incorporation reaction. You have a strand, you have a primer, 3' hydroxyl group 3. The new nucleotide comes, forms the base pair, correct? This is triphosphate 3' hydroxyl group with the help of polymerase, with the help of magnesium ion. pK is decreased, so you attach the alpha phosphate of the deoxytriphosphate, nucleotide triphosphate, and forms the phosphodiester bond. That's nucleotide incorporation. And if there is a mismatch, like here, you see GC is common. If there is GT incorporation mismatch base pair, it is melted and removed. Because think about this, you have maybe in E. coli, the whole cycle is 20 minutes, 15-20 minutes. You have to replicate about few million base pairs within maybe 1 to 2 minutes, because that's the mitotic phase, correct? Rest of the mitosis is very small. So within 1 to 2 minutes, you have to do such a big nucleotide incorporation reaction and finish it. And then it is just correct. When you are rushing in the end of the exam, you do a lot of mistakes. Correct? I don't look at the mistakes. I try to understand if your concept is clear. Okay? So when you are rushing, it does the mistakes and it has to be corrected. So that's why DNA polymerase are evolved to take care of the polymerase mistake with the help of this proofreading activity. If there was no proofreading activity, we possibly don't live up to 90, 100 years. Correct? People will have cancer at the age of early childhood because there are so many replication errors and they are not corrected. Now think about RNA polymerase. RNA polymerase does not have this proofreading activity. Correct? DNA polymerase needs the proofreading activity because you need to correct the DNA, genomic integrity. Genome has to be correct. Otherwise, next progeny, correct, will be mutated. We start with dinosaur, it may be snake. It's not that fast, but with lots of mutation, correct? So, RNA polymerase does not have this proofreading activity. Why? How does it handle?
Because you can more easily take care of like misfolded proteins and stuff like that.
That is true, because if you think DNA is the genetic information, it needs to be passed generation. So they have to be 100% correct. But when you think about RNA transcription, DNA is transcribed into RNA, RNA is transcribed into protein. But half-life of this RNA and protein is very short. So even if there is a mistake, correct, it can be degraded out, it should be eliminated. It does not affect the heredity. But if there is a mistake in the protein, crucial protein, it causes human disease. correct? If it cannot be eliminated, if there is wrong protein or wrong RNA, normally cell try to take care of it, degrade it. If it cannot degrade, it accumulates. Then it's a variety of human disease. Can you name a human disease which is caused by abnormal protein degradation? Alzheimer's is one of them. Correct? There are some proteins get deposited in the brain because of the abnormal conformation. They cannot be eliminated. So if they deposit in the brain, eventually they block the function of the neuron. Neuron do not connect. Correct? So when we know your name, I know that my neurons are connected. Correct? But if it is not connecting, I maybe, oh, I know you, but I think I'm getting some of that now. I'm forgetting very often. But that's why people say that it's good to keep learning till the rest of the life. Did I tell you a story of the old piano? Never? Okay. I was shopping for an old piano because new piano is very expensive and my daughter wanted to learn. She was 5, 6 at that stage. So I was not sure whether she likes to learn for the rest of the life and so on and so on. I did not want to spend much money. You know, we don't make also a lot of money. Right? So you have to always worry about, so do we invest or not? So always I look at the tag list. Correct? For a used piano, in fact, if you are buying a musical instrument, tag list is a good site. And I have some fascination and I sometimes keep buying. And I have a lot of good instruments which are very, very good. It's better than the sometimes new one. Okay. So I was looking for a used piano. I went for this used piano shop. They have some, and it does not play so good. And at the end, in the Mansfield, I went to somebody's home to look at the piano. She has a nice piano. She's a little bit old, maybe 80, in that range. So she has a cat, a dog, and a piano. Correct? But she cannot, if it possibly wants to give it. I like the piano. I said, how much would you cost? She says, about $150. I said, why so cheap? Then she says, it's because your daughter is learning and I don't want to, correct? Keep it, so take it. Then I was there and she started talking, what you do, and I said, I'm a biochemistry professor at UK. And her said, wow, biochemistry, I think of, she was telling that she wants to take some undergraduate biochemistry course at UK. I said, well, why you need to take biochemistry course now? Because I did not tell that you are so senior, but it's obvious she does not need a job, she retired, she has plenty of money. Why she wants to take a biochemistry course? She says, I want to keep learning. Okay? She wants to take a class just to keep his neurons active so that she does not get Alzheimer's. Does it make sense? So it was very interesting for me, eye-opening, that how this correct learning keeps you active. Normally people who have this problem with the memory, they're encouraged to learn. Irrespective of what you learn, just learn. Whether it's music, I think music is the best because you tend to enjoy. So keep learning, reading music, and you know that if you are learning, your neurons are healthy. So why I am telling the story of this? You know? So, the malfunction of the protein. Correct? Neuron connects. So you start with sometimes, somewhere, and go somewhere and you don't know. Yes.
So, do you play any instrument?
We can talk that later. Yes, I do. Okay, so so lot of stories comes, but let's focus on studies. Otherwise, I'll be lost and correct. So you need to have proofreading, and it is critical in case of DNA because DNA is the hereditary material, and which is not so important in case of RNA polymerase transcription or translation. Correct? So these are all interesting stuff. In fact, if you take my metabolism and regulation class, we talk about a lot of these cell signaling pathways, human disease, neurological disorder. I think very interesting. Okay, so at least I convinced you that you need proofreading, and this is 3' to 5' in exonuclease activity, and this is present in DNA polymerase 1. DNA polymerase 1 is the polymerase which was first discovered, correct? First DNA polymerase isolated, and which was used to demonstrate that DNA replication is real in test tube. Who is the scientist? Arthur Kornberg, correct? What is the year of Nobel Prize? 1957. So get a little bit of the, the history. You start with Charles Darwin, Mendel, 1860s. Then you look at what are the major discovery. Actually, there are few, very few discoveries which stand, correct? Like the Empire State Building in New York, correct? There are a lot of big buildings, only few buildings are noted, correct? You can see from the outside. And DNA polymerase, discovery of the DNA double helix, discovery of the DNA polymerase is one of the big buildings, correct? What is the next discovery which made a huge impact? So this is 1957. What is the next major discovery which impacted biomedical science? Come on, guess something. PCR is what is the time frame? About I think the Nobel Prize is 1987. Who is the discoverer? We'll talk about. You studied the PCR in Biochem 1.
Recombination?
Recombination, yes, very important. But PCR you studied in Biochem 1. Kerry Mullis. You should read the biography history of this discovery. Then that was a very interesting discovery. It was a very bright scientist, correct? But scientist does not make money, correct? So he wanted to make some money. He got bored with his publication. He joined in industry, correct? So normally the creative people get very easily excited and get very easily bored. After some time, initial wow, right? They get excited, do something. After a couple of years, no, it's not so good. They get bored and frustrated. So after making a lot of money, he was getting bored, so he thought, okay, let's get rid of science. He opened his own bakery. You read the story, it's very interesting, some of these creative people. Of course, he cannot survive without science, baking the bread. So he again went back. And that's how he discovered the PCR technology. Okay, so very important. So DNA polymerase 1 is the enzyme which is discovered in 1957 by Arthur Kornberg, and who demonstrated that DNA replication is feasible in this flow. You take a template, take a primer, add the polymerase, add the nucleotide phosphate, add the magnesium ion, you would produce complementary copies of the DNA in test tube. Now, DNA polymerase 1, there are several DNA polymerase in E. coli. E. coli we talk because this is what the initial studies are done. So there are DNA polymerase 1, which was first discovered, and actually this is one of the most abundant DNA polymerase. And later on it was realized that there are other DNA polymerase, all 2, all 3, and now actually all 4 and 5. These are all E. coli different. And this E. coli DNA polymerase, all of them are DNA polymerase. They have all active sites, polymerase active sites. They have 3' to 5' exonuclease active site. Some of the polymerase also have this 5' to 3' exonuclease active site. What it means that this polymerase hydrolyze the nucleotide starting at the 5' end of the DNA. Does it make sense? So this is at the 3' end. And Pol 1 appeared to have all 3 activities. Pol 3 has polymerase active site activity and this. Pol 2 has polymerase activity. In fact, I think it has exonuclease activity. I don't remember which one it is. Okay. So we already understand that Pol 1, polymerase 1, discovered by Arthur Kornberg, he actually thought that this is the real replicating DNA polymerase in bacteria. But later on it was realized not the Pol 1, Pol 3 is the major replicating enzyme. Pol 2, Pol 4 and 5, they are primarily involved in repair. Let's say there is damaged DNA. It removes the damaged nucleotide, so there is a gap which starts to repair. There actually some of this comes into play. So, but Pol 1 has all 3 active sites, 3' to 5', and we know the activity, this activity is nucleotide incorporation, correct? Nucleotide incorporation, correct? The function of 3' to 5' exo is what we discussed. Proofreading. Correct? Proofreading. So, what is the function of 5' to 3' exonuclease activity? So, this is the replicating DNA polymerase which is present in the replication fork. So, you need the nucleotide incorporation activity as well as proofreading activity because if there is a mistake, it needs to be taken care of. Does it make sense? So, what is the function of 5' to 3' exonuclease activity? So, for DNA replication, you need a template, you need a primer with hydroxyl group, 3' hydroxyl group 3. Does it make sense? Now, in vivo, if you are in vitro means in test tube, you could supply a DNA, you can supply a synthetic oligonucleotide primer and do the reaction. But inside the cell, right, we don't have the synthetic DNA which can act as primer. So what it does, let's take the example of something like that. So you have these Okazaki fragments. This is 5 prime, 3 prime, Okazaki fragment, and this is your the leading strand. Does it make sense? So for the leading strand, you need just one primer to start with. Does it make sense? And once you supply this primer, it will keep on going. In case of lagging strand, because you are starting the DNA replication every time it's new, you need some primer, and this primer is actually a short RNA based primer. So there is, every time a new synthesis is taking place, at the 5 prime end, the starting primer is actually a short RNA. There is an enzyme which is called primase, which helps the synthesis of the RNA primer. Correct? So you need a primer. In vivo, inside the living cell, this primer is actually the short RNA molecule, and this RNA acts as a primer, and this RNA is synthesized by an enzyme called primase. Does it make sense? So this is your 5 prime end, this is 3 prime end, so 5 prime end always has the primer, RNA primer. So when this Okazaki fragment needs to be joined together, these RNA primer at the 5 prime end needs to be removed. Does it make sense? So you have, this is your, this you need, this is 3 prime end, this is 5 prime end. These RNA primer, they are located at the 5 prime end, needs to be degraded out. And this RNA primer degradation at the 5 prime end, correct, is controlled by the 5 prime to 3 prime exonuclease activity of Pol 1. Does it make sense? So remove these RNA primers. So you remove these RNA primers. Make a gap. Does it make sense? So you have removed the RNA primer from here. So you have created some gap. So these gaps needs to be filled. Now it's not a problem because this is your 3 prime end, which has a hydroxy group. So this end is further extended. Correct? With a new nucleotide incorporation. Does it make sense? Yes or no? So eventually, you produce Alright? This type of end, this is a extended new nucleotide. This is 3' end. This is 3' end. So this gap is filled. There is a need. The gap is filled. So this process is called nick translation, or also called basically gap is filled. Does it make sense? So you need a polymerase activity of pol 1. Again, pol 1 is involved. This nick translation is caused by pol 1, polymerase 1, and here it is just the polymerase active site activity. Does it make sense? So once it is filled, then these two end 5' end and 3' end is joined together. How? What is the name of the enzyme? Basically, it's ligated. So, correct? You ligate. This is it clear? Yeah. So, polymerase 1 is primarily involved in removal of the RNA primer. Let's see if I have. Yeah. DNA pol 3 uses the RNA primer because that's where it is synthesized. A special primase forms the required RNA primer. Pol 1 excites this primer. Does it make sense? DNA ligase seals the nick between Okazaki fragments. So you have removal of the RNA primer, nick translation, which is gap filling, correct? And then ligation is produced continuous form of the complementary to the lagging strand. This is a complete picture of a replication fork. Replication fork means the active replicating enzyme. Okay, let's turn off the light. So this is the double helical DNA. Double helical DNA. This DNA needs to be opened up to the single stranded DNA. And the enzyme which helps the opening of the correct DNA is called helicase. It opens the helix. So you need a helicase to open. Think about taking a two-state rubber band. I wish I had a rubber band. I should have got. Alright? Anybody has a rubber band? No? Don't tie your hair. Okay. So rubber band, if you have, is I'm not so good in drawing. Alright? Not too bad. So if you open up here, correct? The supercoil, the spiral gets condensed, goes towards the end, correct? They become highly strained because you are not opening the helix, correct? So eventually you get highly strained supercoiling towards the end, and that cannot sustain. You need some enzyme to remove the supercoiling, and that includes topoisomerase and some gyrase kind of enzyme which helps to relieve the supercoiling strain. Does it make sense? So you need a primase, you need a helicase to open the helix to single stranded DNA. You need gyrase to relieve the strain. You need a primase which will supply the RNA primer. This is RNA primer, correct? So this enzyme is needed. There are polymerases which you need. there are two copies of the polymerase which help the replication, one for the leading strand, one for the lagging strand, but they are interacting each other. So this is the where replication is taking place. Okay, so there are two copies of polymerase, one for the leading strand, one for the lagging strand, and this polymerase is actually DNA polymerase 3. I think some of you are tired, just be a little bit because, right? Don't sleep. So this is DNA polymerase 3. Which are bound at the replication for replicating DNA. Does it make sense? And we discussed in helicase to open the helix, in gyrase to release the state, in the primer to supply the primase. Every time you have a new Okazaki fragment, you need a new primer. Somebody has to supply that. Without primer, it cannot replicate. So this primer is supplied by primase. It is already supplying the primer for new one. Okay. Now, once the helicase opens the single-stranded DNA, it has to hold it single-stranded until the replication is complete. Does it make sense? So there are a lot of proteins in the cell which are kind of single-strand binding protein. Do you see here? These small stuff, these are called single strand binding protein, SSBs. So once the helicase opens the DNA to make a single strand, SSB, the single strand binding protein, comes and binds the single stranded region of the DNA and stabilizes. That helps, correct, the time for DNA replication. Does it make sense? So single strand binding protein stabilizes, and what else we need? So this is kind of the structure of the replicating end of the DNA, which is called replication fork. Now you synthesize this Okazaki fragment, and Okazaki fragment needs to be connected. We discussed that you need to remove the RNA primer, and DNA polymerase 1, 5' to 3' nuclease activity, removes this RNA primer. DNA polymerase 1 also seals the gap because there is a gap, and then comes DNA ligase, which connects the two ends of the Okazaki fragment. So this completes the total different proteins, basic or minimum requirement for a replicating DNA polymerase in vivo inside the cell. There are other proteins also involved, but this is basic. Correct? So I may ask in your exam, draw a functional replication fork. Correct? So that means we need to draw and write the name of the proteins which are involved and briefly tell me what is their function. Does it make sense? Yes or no? Pretty easy. So let's review a couple of stuff. Okay. So 3' to 5' exonuclease activity of the DNA polymerase 1. Correct? Removes the 3' end of the growing chain. So when it is replicating, again there will be mistakes, so that's why the proofreading activity is there. And so Pol1 has three different types of activities. One is polymerase activity, which is involved in the nick translation or gap filling. It has 5' to 3' exonuclease activity, which is involved in the removal of the primer at the 5' end of the Okazaki fragment. It has 3' to 5' exonuclease activity, which is responsible for its proofreading. Pol1 is a big protein. The 5' exonuclease activity, okay, works with the Nix translation. There is something called clino fragment of DNA polymerase 1. Okay, Hans Clino used the enzyme called trypsin, which proteolyzes the enzyme, and it cleaves between 323 and 324 amino acids, separates 1 to 323 and 324 to 90. So you have a big protein, pol 1, correct? It is 928 amino acid, correct? What is the molecular weight approximately?
110.
How much? How much is the approximate molecular weight of DNA polymerase 1? If it is 928 amino acids, approximately. We will ask this question in the exam. How much? One amino acid is approximately how much?
110.
About 110 Dalton, correct? So you multiply that with 110, so it's approximately 100 kilodalton. It's pretty big protein. 100 kilodalton is a pretty big protein. So you could trypsinize this one. So this is 323. So trypsin, correct? We produce two fragments. One is N-terminal small fragment and another is big fragment, which is called the clino fragment of DNA polymerase. This fragment actually contains the DNA polymerase activity, clino, but it does not have the exonuclease, 3' to 5' exonuclease activity. Now 5' to 3' exonuclease activity is present in the N-terminus and two other activities. So this is 5' to 3' exo, this has pol plus 3' to 5' exo. This fragment is called clino fragment of DNA polymerase. Lot of you, when you are doing the biochemical experiment in the lab, often you will want to radiolabel your DNA by using this Nix translation. Okay, so basically, if you have restriction digest which has this kind of mismatch end, you have studied the restriction digest, correct? With the overhang, you can fill up this with a radioactivity, correct? You supply radioactive nucleotide 32P, alpha 32P, DATP, and clino, the 3' end will be filled, correct? So you can radiolabel the DNA fragment. Normally use this clino fragment of DNA polymerase, which is further mutated to remove the exonuclease activity. Okay, so you will have a polymerase fragment which is only DNA polymerase activity, which is good for labeling DNA in vitro and so on. Correct? Lot of biochemical experiments are done where you need the DNA to be radiolabeled. Tom Stites, Yale University, one of the most famous crystallographers, protein crystallographer. Okay, he is the one first time who actually solved the structure of clino fragments got Nobel Prize, I think 3 years ago, 2011 or something like that. There are 3 guys got Nobel Prize solving the biomolecular, macromolecular crystal structure. Look at these beautiful, correct? Highly symmetrical crystal structure of this DNA polymerase. Correct? This is the DNA which is going to the end to inside. So beautiful. Lot of time these proteins crystals are highly symmetrical because that's how it likes to crystallize. Extremely difficult to crystallize. But if you get a crystal, right, you can get a cover page of the journal. Correct? So this picture, you see the cover page of many biochemistry books, including the biochemistry book by Stryer. It's a fantastic biochemistry book. So Tom Stey's lab is one of the big labs in protein crystallography, Yale University, who does a lot of the protein. I think right now, I think they are pioneers in crystallizing the ribosome particles, which are RNA protein big complexes, which are involved in translation. Extremely difficult, extremely complex, correct? Big macromolecules, but they are able to do. The crystal structures are very important because it gives you the structural information, correct? RNA polymerase crystal structure got Nobel Prize solving RNA polymerase 2 from East got Nobel Prize in 2006. Because once you get the crystal structure, right, you know its kind of active site where they are located, what kind of inhibitors you want to design for this particular enzyme, correct? DNA polymerase inhibitors actually pretty good. Antibiotics. There are a lot of antibiotics which we use. They inhibit the growth of bacteria, correct? How do they inhibit? They bind to many of them bind to the DNA polymerase and stop the replication. Does it make sense? Rifampicin, I can list many antibiotics which bind to some part of the active site or allosteric site and stop the DNA replication, inactivates the DNA polymerase. So that's how some of the antibiotics stops the replication of the bacteria. Does it make sense? So crystal structure is very, very important to understand. Not the structure, but the function of the molecule. But there is certain limitation of the crystal structure. What is the limitation? Crystal structure gives a snapshot, correct? How enzyme looks like. But there are certain limitations of crystal structure based information. What is that?
Shell movement.
Slow movement. Kind of you are close. Crystal structure is a kind of snapshot, correct? Think about your photograph. You are standing like that, correct? You take your photograph. We are thinking, wow, hands are always like that. Correct? But it's not true. I am dancing and all kinds of stuff, and crystal structure cannot give that information, the dynamics. But it tells you how elephant is. But all the different conformation of the dancing pose of the elephant or the dancer, right, is not coming out of the crystal structure. Real time. You need some solution based structure determination method. What solution based structure determination method we could use? Can you tell me technique which can give you the structure of the molecule in solution? Any idea? There are a lot of methods, but I think one of the major methods is nuclear magnetic resonance, NMR. NMR gives the structural information, but there is limitation because NMR can handle pretty easily if the molecules are small. But if there are too big molecules, lots of protons, it will go crazy. Correct? We cannot assign where from the signal is coming. But now actually lots of good methods, advanced NMR techniques are coming. There is a Nobel Prize last year. Last year? Yes, last year. Which actually the Nobel Prize, I think it is in chemistry or medicine. Can you tell me the topic? I don't remember the name of it. They gave the Nobel Prize for the cryo-electron microscopy. Cryo-electron microscopy, that means at low temperature, you can image the structure of a molecular complex, a protein. Correct? Sometimes you cannot crystallize a big molecule. So what to do? So these people discovered a microscope where you freeze the protein at very low temperature so that it, correct, does not have the movement, and you can look at under microscope, image the kind of three-dimensional structure. That was Nobel Prize last year. Correct? So structural information is very, very critical, and Tom Stiles, you know the name because he's one of the Nobel laureate, big crystallographer. In fact, if I was starting my career right now, maybe I would have been interested in protein crystallography because the structures are so beautiful. Correct? I think we discussed some of these. Double helix must be announced by helicases, supercoiling must be compensated, DNA direct, replication is semi-discontinuous, leading strand is formed continuously, lagging strand is formed from Okazaki segments, correct? And so on. All three uses RNA primer, a special primate forms the required primer, DNA pol 1 excites the primer, DNA ligase seals the niche between Okazaki segments. Does this statement make sense? Yes or no? Pretty easy. DNA polymerase 3, at least 10 different subunits. We are not going into that detail, but at least I want you to know the image of a replication, functional replication form. Correct? I think that's all about prokaryote. Next class will briefly touch base on eukaryotic DNA replication. Not in detail, at least you need to know in prokaryote. The chemistry is same, prokaryote and eukaryote. But eukaryote is much more evolved and complex. There are a lot of other functions.